Welcome everyone to the next student competition paper. It's by Jaromír Janisch on classification with costly features. So go on, the floor is yours.
Thank you, Václav. So this is a topic which I worked on last year, which resulted into two papers. One was in Triple AI 2019 conference, and subsequently we improved it, added some things, and it was published in a machine learning journal in 2020. So this talk will be mainly about the full featured version from the journal, but I have to start with the basics. What is classification with costly features? So classification with costly features is a simple thing. In normal classification, you have a sample and you have to assign it with a label, right? Easy. But here, you actually don't know the features up front of the sample. So the objective slightly changes because of all the features have also associated cost, and you can ask for them, but you have to pay the cost. So the objective in the end is, in the normal classification, just to minimize the classification loss, as you see on the left side. But here you also need to fit into some budget which is given. And so on the right side, you see the mean of the expectation of the all costs over all samples. It has to fit into some budget B. And I'll take this moment to emphasize that this is not feature selection, because our algorithm can select a different set of features for different samples. So for sample A, you select a totally different set of features than for sample B. All right. So if you see the equations carefully, they are in expectation. That means you care about whole data set at once after, yeah. So we actually derived several approaches to this problem, and one of this is lambda specified budget. So instead of having this straight constraint that the expected cost of features have to fit into a budget B, you can do something like this, that you minimize the loss and the cost of the features altogether. All right, and these two terms, on the loss of the left side and the total cost of all features for that current sample X, is weighted by factor lambda. So if you think about that, the lambda is a trade-off parameter where if you set it to 0, that means that you disregard the cost at all. So you only care about the classification loss. That means probably maximizing accuracy. And if you put it to infinity, then you care only about the costs. So that would mean that you probably don't select any features at all and just classify based on the prior probabilities of the dataset. So these edge cases are not really interesting. So we want to be somewhere in the middle. So how did we approach this particular setting? It can be shown that this objective can be really easily transferred into a Markov decision process, in which a state is defined as a currently observed features of the sample. In one episode, you classify only one sample, right? And the states of the episode incrementally disclose features as the algorithm asks for them. And at the end, the classification occurs. So at each state, you have a set of actions which there is one action for each feature which is unobserved. So the algorithm can ask them. And there is also a set of actions that lead to classification. So if you carefully like create a reward function such that for each action that reveals a feature, a reward of minus lambda cost of that feature is given, then you can see that during the whole episode, the total amount of this reward is exactly this, is lambda, and the total cost of all features which were retrieved by the algorithm for that particular sample. And if you give a reward of minus loss of the classification at the end, once during the episode, then that's exactly this term here. So as you can see, the total reward per one episode is at the bottom here, and it's exactly what we want to optimize as this thing, this expression up here. Just a minor difference, that the above objective is in expectation, and here we have a reward which is given for one episode. But if you use standard reinforcement learning algorithms, what they do, they maximize expected reward. So in the end, since they maximize expected reward, that's exactly what we want to achieve. That's the minimization of the objective above. So what we do is we use reinforcement learning algorithms. We use deep reinforcement learning algorithms based on neural networks. And in this case, I won't go into much detail here because that's just a machine. The neural network is just a black box which gets some input and spits out some outputs, and it's trained by standard deep reinforcement learning algorithms, which were developed much earlier than this technique. So I won't go into details there, but show you some results instead. So what you can do is that you can sweep through the lambda interval. So for example, from 0 to some defined value, and you can plot the results of for each lambda you train a specific model, and you can plot the results on this plane where the x-axis are the used features or the cost, and the y-axis there is accuracy of the model. This is the result for MNIST dataset, which are you probably familiar with. And in this case, we used just the cost of 1 for every feature uniformly. So on the x-axis, we can, instead of cost, we can say it's the number of used features. So the black line is our algorithm, and you can see that here on the about 50 features out of 700, the algorithms achieves about 95% accuracy, which is a nice achievement. The budget prune is a formal algorithm, which is previous state of the art, nothing to do with our algorithm, but it's included here to see that there is some improvement in the quality of the solutions. And the top line here, the dashed top line is just a plain neural network classifier that is given all the features at once. And you see that our algorithm, even with all the features, exceeds the performance of a neural network classifier. And that's because it generalizes better, but again, I won't go into much detail here unless you ask later. So that's classification with costly features. It's a very simple thing, and you can also do something like this. You can, for example, here this is the MNIST data set where there are the classes from 0 to 9 averaged all over the data set. So this is like average 0, average 1, and so on. And the green dots show the spots that the algorithm asks, and the brightness is like a frequency of how many times the algorithm asked for that particular feature or the pixel at this particular class. So without explaining too much, it's clear that the algorithm is much more explainable because you can see which pixels or which features contributed to the solution. For example, in this 4 and 9, you can see that algorithm asks in this area where the 4 is black. The same thing happens here in 9. This is to distinguish these two numbers. So in this sense, this is much more explainable. So we took a step further. So the thing is that user usually don't want to set some artificial parameter lambda, right? He wants to have a budget 200 and give me the lambda that corresponds to this value. But unfortunately, in the previous version of the algorithm, you can only do things like you set some lambda, train a model, and see what budget it achieves. So then based on the result, you can maybe change the lambda, fully train your model again, and achieve a different budget. And by this iteration, you can converge to some area close to your budget you defined. But given that the training of the algorithm is not exactly free for one instance, and you can't really parallelize this to some extent, yes, but still you need to see the results before to accommodate for that, to change the lambda. This is not very nice approach. So we took a step forward or back, as you want to think about that, and we started from the original equation. So we want to minimize this expected loss, and it is constrained by this inequality right on the right. So the expected cost overall samples has to be with some budget. And it can be shown that this particular type of optimization problem, which is constrained by some inequality, can be transferred into a Lagrangian function, which is shown here. It's the L. It's a function of two parameters, theta and lambda, and it's written right here. So the function is very similar what we did before, but there is some slight change here. That's the lambda scaled the cost of the sample minus the budget. And if you find a saddle point of this function by maximizing lambda while minimizing theta, then you arrive at some fixed point of the function, and it can be proved that this point is the optimal solution for the original problem. So inspired by, yes, hello?
Are you sure that it's correct without convexity? If the functions are not convex, I don't think that's true.
Yeah, maybe there are some assumptions to that, but in our case, it holds. Yes, you are right. It doesn't maybe hold in the general case. All right.
Yeah, I guess that you could assume the empirical risk minimization at the top level or such. So
let me continue and just maybe get to it back later. All right. Okay. So based on this result and inspired by some other research which work with this idea, we can do gradually find tune lambda by following its gradient. So the gradient of the Lagrangian with respect to lambda is really simple. It's just expected cost of samples minus the budget. So the gradient is really simple. And on the other side, to minimize the Lagrangian with respect to theta, we can rewrite this this expression on the right, and you can see that it's this expression minus lambda b, and lambda b doesn't influence the solution with respect to theta. So if you look carefully on this expression here, it's exactly what we had before. So in the lambda specified budget. So you can use normal reinforcement learning as we did before to optimize Lagrangian with respect to theta. But the difference is that you don't do full training and full sweep, full follow of the gradient with lambda and with theta, but you take just small steps in repeatedly optimize lambda, optimize theta, taking small steps, and you gradually can achieve to the stationary point of the Lagrangian. There are still some theoretical questions where this holds in the general, but in practice it actually works very well. And you can see here that that's a different data set that we trained several algorithms for different budgets. There is like 5 runs for different budgets, which you can see by these vertical lines. And here you see the clusterings of different runs, which are color coded for different budgets. And you see that they cluster around the budget which was specified. So that's experimental result that it works well. And if we look at the training itself, then we have 3 graphs here, which top one is how the lambda evolves through the time. The second one is the cost, how it evolves through the time, and the budget here is set to the 10. And the third graph is accuracy, how it rises over time. So you can see that the cost oscillates around the budget which was set, and it's gradually, the oscillation gradually diminishes, and the lambda accommodates gradually to changing model, because as you change theta, you change the model and you have to change lambda accordingly. So that's another achievement of our research, which was published in the Machine Learning Journal. And that's actually not all. So there are many other things which were included in the paper. And for example, we have per sample hard budget settings. For to give it in contrast, before we talked about average budget setting. So for one before you had maybe for some sample you don't need all features to fit in the you don't need all the features, you just need some. So that maybe gives you a really small cost. For some samples you need a lot of features which exceeds the cost, exceeds the budget to classify it correctly. But on average you have to fit it in budget. So this is a different setting where you have a straight, direct, hard budget for each sample. So for each sample X, you have to fit within the budget. And this is the setting, for example, if you think about that you have a phone and you want to classify that some file which you downloaded from the internet is malicious or not. So you send it to some server and it has to return a response within 2 seconds. If it doesn't, then the user uninstalls the app. So this is exactly the setting. And we show that by modifying the original MDP, so the MDP by itself enforces this constraint, and there is no lambda at all, you just enforce it within the MDP. So basically, when the budget is reached, the classification has to occur. This is the only action. Then it actually works. It works well. Again, we compared it to some prior work and showed that that it outperforms the prior work. So another setting is that you actually don't have a full data set. You have a sparse set. This is setting in. You have a lot of historical data from tests performed on patients, but you cannot go back and do another test for a patient which is simply not there anymore. So but in the evaluation, in the production, you can of course do whatever you want. You can ask any feature you want. So this is a setting with sparse training data sets, where we again approach it in a principled way. You can enforce in the MDP itself that some actions are not available. So the actions which corresponds to the features which are not available simply do not exist. And we again compared it to common imputation strategies used in medicine. So one of them is straightforward mini imputation of the features, and then you train with just the data set. The second one is called MNIST. This is more sophisticated imputation strategy where you iteratively do some linear regression on the missing features, and again you come up with a full data set which you train on, and then you say this is my model. And we again say that for when there is a substantial amount of number of features which is missing, then our approach works better. And the last setting which was included in the conference paper is that you can actually include other classifiers into that as features. So for example, you have a legacy classifier at your problem that works very well for some feature space, right? And you just can plug it into our algorithm, and our algorithm will automatically determine which state space this is relevant for, and if it's justified the cost of running this legacy classifier, and automatically will call it and use the result as information to decide its own classification results. So this is another, I think, great achievement. So I want at the end of the presentation, I want to just mention a little bit about impact and applications of our research. So as I said, this was accepted to AAAI 2019 and subsequently into Machine Learning Journal in the next year. And I usually start this presentation by giving a clear motivation why this is a good thing to do, why this is a good thing to think about and do the research at all. But since the paper was out for some time already, I don't have to do that anymore, and I can speak. I can let the results themselves speak for themselves. So these two papers acquired, according to Google Scholar, 59 citations, and were cited by papers which were in many different areas. So for example, there are 14 applied medical papers that cited this research, and that makes me very happy that somebody somewhere is maybe using my research to, I don't know, maybe help people. Other citations include areas like network security, surveillance, data analysis, even things like meteorology or activity recognition. So that's I think like a huge success of the research, and that's basically it. So thank you all for your attention, and if you want to see the code, it's publicly available on my GitHub site. The papers at the conference are publicly available for the journal. It's behind us, I think, a paywall, but you can ask me, or you have your own university subscription, right? So last few words. This is work of me, my colleagues Tomáš, Pevný, and Viliam, Lisý. which you probably know very well. And that's really all for me right now. And if you have any questions, I'm here to answer them.